So, now we are going to talk about adiabatic work. So, what is an adiabatic work? Adiabatic work is where you have no exchange of heat, and I am going to just derive that adiabatic work here. So, du equal to dq plus dw. In case of adiabatic, dq equal to 0. So, we are going to have du equal to dw for adiabatic case. Now, we know that for an ideal gas we can write du as Cv dt. Now, given a temperature difference. So, in adiabatic case, of course, then if there is a work done, that means some value of W is there, then you see that Cv, because Cv is taken to be constant, temperature is going to change, and that is the reason that in adiabatic case the temperature changes. And how much is the work done, that will depend on how much change in the temperature is happening. Let us say the temperature is changing from T1 to T2. So, in that case total change in U will be integration of Cv dt from T1 to T2, giving us Cv T2 minus T1. And since this is the amount of work done, so if the work done in adiabatic case is nothing but Cv T2 minus T1. That is when you write the work in terms of temperature. However, if you want to write that work in terms of pressure and volume, you are going to do a little bit more work, okay? And that is what we are going to do now. So, let us go back again. So, now we know that du equal to dw for ideal gas, or Cv dt equal to minus P dV. Now, for ideal gas we know that P v equal to nRT, P v equal to nRT, and therefore, I am going to replace P by nRT by V. So, Cv dt is equal to minus nRT by V dV, but left hand side I have a dt, which takes care of temperature change. So, I have to bring this T below here, because there is a function of temperature. Cv dt by T is equal to minus nR by V dV. Okay. Now, I can write Cv dt by T is minus R by V bar. V bar is V by N, molar volume dV. Now, I integrate both sides. So, when I am integrating from T1 to T2, what I am going to get is Cv ln T. So, it is it was correct actually, T2 by T1, it was correct. Right hand side is minus R ln V2 by V1. I will put the bar. So, now you see I have to equate them both. So, in that case I am bringing Cv down below. So, ln T2 by T1 is equal to minus R by Cv ln V2 by V1. And what is R by Cv? So, R by Cv is Cp minus Cv equal to R, right. Divide both sides by Cv, you will get Cp by Cv minus 1 equal to R by Cv, right. So, R by Cv is Cp by Cv minus 1, and Cp by Cv is typically called gamma. So, gamma minus 1 is R by Cv. So, we can now write that ln T2 by T1 is equal to minus gamma minus 1 ln V2 by V1 bar. Okay. If I have a little bit more space here, I will write it. So, how much we got? We got that T2 by T1 ln T2 by T1 was minus R by Cv ln V2 by V1. This was we had, and we showed that this is nothing but R by Cv ln, this was bar V1 by V2, okay, which means ln T2 by T1 is equal to ln V1 by V2 to the power R by Cv, and we know that R by Cv, okay, we will do that, put the R by Cv later on. So, now when we have this equation, both sides ln is there, then we can write T2 by T1 is equal to V 1 by V 2 to the power r by C V, which I have calculated to be gamma minus 1. So, this is the equation we have, but we cannot forget the first law of thermodynamics. Sorry, we cannot forget the equation of ideal gas. What was that? P v equal to nRT, that is always there, or P v bar equal to R T, which means if I have T 1, then I have P 1 V 1 bar, and if I have T 2, then I have P 2 V 2, right. Now, let us take the ratio of T 2 by T 1, what I am going to get? P 2 V 2 bar by P 1 V 1 bar. Okay. Let us put the equation 2 in equation 1. So, T 2 by T 1 I am going to replace that. So, P 2 V 2 bar by P 1 V 1 bar is equal to V 1 bar by V 2 bar to the power gamma minus 1. Now, let us take V 2 to the power gamma minus on the left. Now, let us like cross multiply. Okay. What we are going to get? P 2 V 2 bar into V 2 to the power gamma minus 1 is equal to P 1 V 1 bar V 1 to the power gamma minus 1, or gamma minus 1 plus 1 is like P 2 V 2 to the power gamma equal to P 1 V 1 to the power gamma. So, for an isothermal case, remember what was the case? P v equal to constant, but for an adiabatic case we get P v to the power gamma equal to constant. That is the difference between isothermal and adiabatic case. So, now that we have derived that, let us write it here. So, what we have seen that P 1 V 1 to the power gamma is equal to P 2 V 2 to the power gamma equal to P v to the power gamma in general. Once that is the case, we can always write then pressure as, or any general pressure we can express as P 1 V 1 to the power gamma divided by V. Now, we are going to calculate the P v way, the work done. So, which is minus P d V integration V 1 to V 2, and we are going to replace the pressure from this expression, which is now P 1 V 1 to the power gamma is a constant, right, and this expression is wrong. So, P v V to the power gamma. So, it will be gamma. Okay. You see from this one I am getting it is P 1 V 1 to the power gamma by V to the power gamma, that was the thing. So, now I am getting correct one d V by V to the power gamma, that is fine now. Now, minus P 1 V 1 to the power gamma, when I integrate the gamma, what I am going to get? Minus gamma plus 1 by V to the power 1 minus gamma, going from V 1 to V 2. So, minus P 1 V 1 to the power gamma by 1 minus gamma V 2 to the power 1 minus gamma minus 1 minus gamma V 1 to the power 1 minus gamma. And we can see the same expressions, it is written here. So, we can see that what is the correct one. This is a derivation that we have already done. Okay. So, this is the now expression for. So, you see this is same as that of C v T 2 minus T 1, you know, do not forget that is same as C v T 2 minus T 1. So, if you have the information of temperature, you use this C v T 2 minus T 1 formula. If you do not have the information of temperature, you have to use this complicated formula. Okay. So, now obviously, when you compare between isothermal and adiabatic work, for an isothermal, P v equal to constant, and therefore, P goes as 1 by V, right. For adiabatic case, adiabatic processes, P v to the power gamma is constant. So, therefore, P goes as 1 by V to the power gamma, and gamma is C p by C v, okay, which is R in case of ideal gas, and it will be like more than 1, values will be more than 1 and positive quantity. So, when I plot isothermal and adiabatic, what do you think the profile will look like? Let us say this is isothermal. Will the adiabatic be higher or lower? Just compare these two expression and tell me. In one case it is going just 1 by v, another case is going 1 by v to the power gamma. Since gamma is larger than 1, imagine gamma is 2. So, it is decreasing like much faster. So, if gamma is greater than 1, then it will be always lower. So, this is isothermal and this is adiabatic. So, adiabatic work will be always the pressure fall in adiabatic processes will be always lower than isothermal processes. So, this is the mathematical reason that one is going by 1 by v and another is going by 1 by v to the power gamma. What will be the physical reason for this? The physical reason for this is that in isothermal case, let us say you have a gas system and that is going to expand, but in order to keep the temperature you have a burner kept or a heat reservoir is kept there. So, heat is being supplied continuously. So, because of expansion pressure falls, but because heat goes inside it does not fall as much, but in the adiabatic case system there is no heat going inside. So, pressure is falling accordingly to the expansion volume alone, there is no compensation coming from heat outside, and that is the reason for isothermal processes the pressure is less compared to that of adiabatic processes, and that is shown by this particular nice looking graph where you have not only 2 dimension, but also 3 dimension. The third dimension says that as if when you even change the temperature, then how it will look like. So, that is going to be different. So, that one can study, and reason I have already mentioned. Okay. So, now I think we have crossed the time, but we are going to discuss a few problems or calculations about how to do certain works and things like that tomorrow's class. Okay. So, we will stop here.